Before moving on to the numerical methods that we use in computers, we will talk about the non-computer methods, starting with the differentiation first. So let's check the non-computer method we can use for taking derivative numerically. Basically, for a tabulated data especially, we will have some inputs data and some output data, as you can see here. And we will have a curve of that with these approaches I will show now, which is called equal area graphical differentiation actually. First of all, we will take the delta y divided by delta x, which means that we are actually tabulating the data first like this. Then for each interval, so from 0 to 3 for instance, a divided difference is employed to estimate the slope. So here delta x is 3 minus 0 and delta y is 200 minus 0. If we divide them, it becomes 66.7 for instance. So maybe we can just define that delta x is 3 minus 0 and delta y is 300 minus 0. So the division of these 300 divided by 3, sorry, 200 divided by 3 gives us 66.8. Similarly, between these, so this is delta x is 3 again. Here the delta y is 150, and 150 divided by 3 gives us 50. And if you continue on this, divide 470 minus 350 to this, you will get this, then here, then here. So you get the delta y divided by delta x values. And these are the estimation of the slopes actually. Once you find these, you draw them into the graph. Basically, we will have this 66.7 here. Just plot them here actually. Then have a bar graph of these delta y divided by delta x values. So just plot these values or these lines, horizontal lines, in between axes, because this axis is x-axis. Just use x values here, and between 0 and 3, assume that the slope 66.7. The slope is 66.7, just straight bar. Then go down, then plot 50 between 3 to 6, then go down, then draw a line for 40 between 6 and 9, and similarly 30, then 23.3 between 15 and 18. So you will have a stepwise bar graph, as you can see here. First of all, you will have it. Then you will draw a curved line, smooth curve, which actually passes through the middle points of these drawn lines. So you drew these lines first, then in between the ends, so in the middle points, just plot a curve, as you can see here. So if you use the middle points, that means you will have an equal division of the areas next to each other, or on the left and right side of the curve at each bar, let's say. And be careful that here between 9 and 15 there is a large gap. That's why this has a large gap here. So 30 is for between 9 and 15, simply 30. Okay, now we plotted this curve using the middle points of the bar plot. Now we are going to let's go to the third one, because we said this already. It is drawn so that visually the positive and negative areas are balanced, so these will be balanced. Basically, midpoints is the best for that. And then the values of dy dx, the derivatives at given values of x, can be read from the curve. So let's say for 0 we want to take the derivative. Then from this curve that we plotted, go to 0 at y-axis. It will give us the value. It's 76.5 for instance here, larger than this, and you can get this value. And for 3 here, this value here is 57.5. so when you draw them actually at each intersection of 6, 9, not 12 because 12 is not here, but you can still find it too. It's about 30, and 15 is like 25, and 18 is 21.5. So you can simply find any functions or any values derivative, as you can see here. And this is that simple actually. Just take the delta y divided by delta x at each interval, plot them as bar graphs, then plot a smooth curve that passes through the midpoints, for instance, then take the values for any x value that you want to find the derivative as the y value over here. So this is a three-step process, and it's called equal area graphical differentiation as the non-computer method for differentiation. We have also non-computer method for integration. Let's define that too, and we have two approaches for this. The first one is using grids. So if you have a function or data, just plot it into a graph, then divide the graph into some grids, as you can see here, with equal squares, let's say, and count the number of boxes or grids, the squares, under the function, and sum the grid area to calculate the area under the curve. So simply we want to find the area under the curve in the integration. So you can simply use these square areas and sum them to get the area in between A and B, for instance. If you go to a different value, you can simply add these two, for example. This is a very simple non-computer method that you can use. Another method is using rectangles or strips to approximate the integral. So simply we have a function again. We plotted it into fx and x graph. Then we will have in between A and B, just, when you take A, just get a regular straight line, horizontal, then go to here. So you can simply actually mark the points first on the curve by dividing this area into some segments. Let's call these segments. And you can have an equal line on the left and right side of these points to get the strips here, or bars, let's say. Then calculate the area of these to get the area under the integration in between A and B. You can count the number of rectangles and sum the strip area to calculate the area under the curve, simply. So these are two methods that you can use for integration as a non-computer method. In this slide, we will now talk about the computer methods, and these are called actually numerical integration or differentiation methods. And the numerical techniques has the same spirit as the non-computer methods that we defined earlier. For differentiation, we will use finite divided differences, and this is the most common technique. Basically, we will take the difference between 2 points again as in the non-computer method. And for data with error, an alternative approach is to fit a smooth curve to data with a technique such as least squares regression, then differentiate this curve to obtain derivative estimates. So instead of finite divided differences, you can simply fit a curve. As we did in the non-computer method, we actually draw a curve. You can fit a curve there using least squares, then differentiate this curve to obtain derivative estimates. And for integration, numerical integration or quadrature methods are available. These methods are easier to implement than the grid approach, which is the non-computer approach we defined in the previous slide, and these are actually easier. They are similar in spirit to the strip method. So we showed two methods, the grid approach and the strip method. The grid approach, you need to calculate, sum all the squares. Actually, in the strip method, we have strips and you sum them. And usually the computer methods for integration are based on this strip method. And function heights are multiplied by strip widths and summed to estimate the integral. However, through clever choices of weighing factors, the resulting estimate can be made more accurate than that from the simple strip method. So we can have better choices of the weighing factors or the strips to be able to get a better approximation of the integral. And the numerical integration and differentiation techniques utilize data at discrete points. So if data is available, if we have a data, then they are used directly for differentiation and integration. And if we have a complex function available, which we are not able to solve using analytical differentiation or integration, then we need numerical methods. But for that, we will create a table of data by ourselves using the function. So we will input some input values and get the outputs to get a table of data from that. We generate it, then use it in the numerical method. Let's check this next slide for that. So we will have an example of an integration of a complex function. Basically, we will apply a two-step procedure for the numerical integration. Let's say we have a complicated function. This, for instance, we are not able to take this integral easily. This is very difficult. So we say that we are going to use numerical integration. But for that, we need a table of data. So we create the data between 0 and 2, and we will use strip method. So we will divide it into segments. Let's say we divide it into 4 segments from 0.25 to 1.75, and we can say these are the midpoints actually. And then we plot them here. So from not 0 but 0.25 here. So segment means between 0 and 0.5. Then from 0.5 to 1, it has to be 0.75. Calculated it from the function. And 125 is between 1 and 1.5, middle point. And 1.75 is between 1.5 and 2 here. So plot it. Then you can get the bar plot by simply drawing linear lines between the range of each segment. Let's say the first one is 0.5 to 0 to 0.5, for instance. Second one 0.5 to 1, 1 to 1.5, linear lines crossing these points that we calculated here. And now the summation of these will give us the area under the curve. Of course, there will be some gaps, and these are usual, and we will have a better modification of these to be able to get a more accurate results in the following chapters. But for this chapter, we just wanted to show how we implement a numerical integration of a complex function in a very simple two-step procedure. And if we don't have the function, maybe we only have the data, then we use that data to get the integration. So if we only have the data, then step 1 is unnecessary, just use 2 and 3. But if you have a function, create the data first, then create the plots. And take the integration by summing the area under the curve with these strips. This is the end of chapter 19, and this chapter 19 was about the numerical integration and differentiation, just an introduction to that, and it is in your book, chapter point PT6 and PT61 and PT611. You can read these to have further information about the topics in this chapter. And thank you very much for listening. See you in other classes.